All right, welcome to our 9th video and our last one of electron config, sort of. Our last type of electron configuration, at least. These are orbital diagrams. So, one final representation of our electron configuration is an orbital diagram. In an orbital diagram, every orbital is represented by a box, or in the past I've shown you a line, and every electron by a half arrow, or again in the past I've shown you a full arrow. So, in the past, what I would have shown you is something like this. These were orbital diagrams. Now, I'm completely fine if you draw them like that. That's fine. I'm going to be changing, however, my personal drawing to this. A, this is what I see a lot of people do. B, this kind of helps you keep the p orbitals together. Because with the lines, if you put them too close, kind of have an issue. You know, any space between these boxes lets me know these are different groups of subshells. And then the half arrows are basically because you just ran out of space in the box. But again, I'm fine with this. I'm fine really with any combination. So, 1927, Friedrich Hund developed a series of rules. Now, they were regarding electron configuration, and we typically call them Hund's rules. Well, that's a lie. We typically call that Hund's rule, but there's actually like 4 or 5 that he made. We tend to kind of summarize them all into one called Hund's rule. And in summary, he states that for degenerate orbitals, which again are ones where they're not completely filled, so having 4 or 5 in a group of p orbitals, or 1 in an s orbital, the lowest energy is attained when the number of electrons having the same spin is maximized. Now, remember, electrons try to fill orbitals with the lowest energy. And so this is saying that for them to do that, basically they all need to have the same spin. More so, when they're all having the same spin, at least to start with, that's the lowest energy possible. So keep that in mind. That means that electrons are going to occupy orbitals of the same energy level and shape, again sometimes called shell and subshell, as single electrons before they occupy as pairs of electrons. Because remember, Pauli says that if you're going to have a pair in the same orbital, they got to be spinning in opposite directions. So before any of those are made pairs, they're going to all be single electrons. That way they're not all having to go the opposite spin. So actually what will happen is they'll occupy the orbitals with basically the same spin. Okay? Or, as I've said in the past, all have to be an up arrow before any can have a down. That means another benefit of the box is that for every group of boxes, so there's a group, that was supposed to work a lot better. That did not. So for every group of boxes, again, this represents S, P, and D, and I'm just not going to draw 7 in a row for F. When we're filling these, they all have to have an up before any have a down. So up, 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 because now they're all going the same direction, then down. That means that if we only had 3 electrons in D, that's what it would look like. Or you'd have 3 up arrows. I don't really care if they're next to each other. Most people put them next to each other. I don't know why you wouldn't. Because, you know, technically with 4, you could put it over here if you want. And just don't, but you could really argue that it doesn't really matter. Because they're not in an order. Anyways, all have to be an up before any have a down. So again, if we had 8 d electrons, that's what it would look like. 3 of them would be paired, 2 would still be unpaired. So there you go. That's basically Hund's rule. So for an orbital diagram, basically we use the same process as a full electron configuration in that we start at 1s, we put 2 in the s, etc. We don't have any shortcuts. Except instead of writing the number of electrons as exponents, so 1s2, we draw arrows according to Hund's rule. So be 1s2. You can, actually, I often put 2 underneath it. I end up doing full and orbital. It's kind of up to you. At very least, tell me that that's the 1s. You don't have to put a 2 after it. But there you go. So, as usual, you try this one and the next one. Sorry about that. I'll show you calcium, and then I'll give you the answer for the next one. All right, welcome back. So calcium has 20. So let's start. We got 1s, 2. We got 2s, 2. Then we got 2p. It's got a total of 6 in there. I like keeping the tallies. Ah! Then we got 3s, 2. I just realized I'm not actually keeping tally. So 18, 16, 10, 8, 3p, 6. And 4s2. Now, calcium's kind of a boring one. Sorry for picking it. Because nothing's degenerate. And the biggest part about Hund's rule is when things aren't completely filled. Like if I can stop you midway through a P block or D block, that's where I really get to know if you're doing what you're supposed to be doing. But for calcium, we do fill everything. So that's our orbital diagram. Okay, so now we're going to do, kind of taking it a step further. How many unpaired electrons are in an atom of bromine? So orbital diagrams are very useful for giving you an idea of how many valence electrons there are. Or at least how many there are available to bond. And it gives you an idea of what charge things are going to be forming. So let's start by making bromines. Bromine has 35. Why did I pick such a big one? Oh well. So 1s2, 2s2, 2p6, 4, 5, 6. Well, we'll do 1s2, 2s2, 2p6, and that. Then we got 3s2. You know, hang on. All right. So bromine ends in 4p. And actually, I'll end up having 4p5. So that'd be 1, 2, 3, 4, 5. All right. Anytime we have a box with only one arrow in it, it's unpaired. Okay? Because it's not a pair. So bromine then has one unpaired electron. So that's technically our answer. But I want to take this a step further and give you an idea of what charge it's going to form. Basically, electrons are stable, or their most stable form is when their orbital is completely filled. So that group of boxes all has a pair in it. Okay, that is, again, the most stable. The next best thing for them is to have one in each. Okay, that means that technically one in each is more stable than, well, this. Barely. So that means that, if possible, electrons or atoms will try to fill their group of orbitals. If that's not possible, then they'll try to get rid of some so that they at least have one in each. And if they can't do that, then they're just going to get rid of that whole set of boxes and drop down to the previous one that's filled. So in this case, if it wants to fill everything, it needs to take one extra electron. If it wanted to get half fill, that's kind of what I call it, it'd have to give away 2. And if it wanted to drop down to 3D, it'd have to give away 5. Well, basically the smallest number of those is 1. That means bromine is likely to take one more electron to fill this. That means that bromine's likely going to have a 1 minus charge, which, as all the halogens, it does. So that hopefully gives you an idea of how charges form. Orbital diagrams are very useful for that. But nonetheless, though, that's orbital diagrams. That's how you use them. Thanks for watching.